Thank you for joining. Today I'm sharing a shard manager paper from Facebook. It's a generic management framework for geo-distributed applications. Yeah. Let's first talk about sharding. Sharding is basically slicing a whole big chunk of data to many shards. And sharding gives the developers more flexibility, and in the sharding system, it can scale with the number of clusters. And one more shard can be developed on one server, or depending on their needs, or geo-distributed if it's needed. Yeah, and let's talk about the regional deployment and geo-distributed deployment. As in the picture, we can see if we are doing a regional deployment for a shard system, all data are in one region, and data migrations are happening inside this region. But if we are doing geo-distributed system deployment, shards can move across different regions, and this creates a lot of barriers for this system. So let's talk about barriers for geo-distributed computing. And let's first talk about the availability. Shard availability is a really important feature for a sharded system. And in this picture, we can see that planned maintenance or software updates are about 100%, 1,000 times more frequent than the unplanned failures. For unplanned failures, like a power outage or server crash, that's not something really easy to solve. But for planned maintenance or software updates, because we have knowledge for them, we can plan ahead. But the thing is, existing shard frameworks do not provide sufficient support for geo-distributed applications, and its lack of support for geo-distributed applications and inability to maintain applications available during the planned events. And in the same time, geo-distributed applications are really widely used and is in large-scale internet service. And in fact, 100% of Facebook's sharded applications are deployed to multiple regions. It may not be that geo-distributed, but it's multiple regions. It means you need to communicate through internet. And another barrier is the placement load balancing. Many applications require advanced placement load balancing features, and existing sharding frameworks don't account for the model nature of their workloads. For example, most sharding frameworks used handcraft PLB, which are really easy to start, but becomes really hard to extend over time. And there's many different applications. Like small applications may prefer simplicity, PLB, and in the same time, mega applications often employ high customized features. And attempting to implement all custom features in a single sharding framework makes it really complex. So in this paper, they pointed to hardware constraints and plenty of software goals that a PLB should achieve. First is system stability, and second is server capacity. And for the software goals, you need to reach the goal of region performance, spread of replica class, planned maintenance. You need to support planned maintenance and the unit acquisition, zero host, and global load balancing, and regional load balancing, and parallel shard failover. And for Facebook, now should I call it Meta? But anyway, one of their solution is a shard manager. Actually, it gives availability improvements and intelligence shard placement. Let's take a look at their shard manager. In the center, there's a orchestra which monitors the health and resource consumption of shard assigned or shards that is assigned to the application servers. And on the left side, there's a allocator is also in the SM control plane that is used when a application server fails or its node changes. In the orchestrator invokes all allocators to generate a new shard server assignment. And up there, we can see there's a server discovery system, which basically responds to for which shards and routers request accordingly, and it replies to the application client. And there's a twin down there. It's Facebook's custom manager. It informs the shard manager, task controller for upcoming hardware maintenance events, kernel updates, and container stocks moves via the task control protocol. And we do have, they also have a zookeeper to store the orchestrator's present state, and during the start of application server release is shard assignment from zookeeper without dependency on the SM control plane itself. And it watches the SM library created nodes in zookeeper to detect failures of application servers. So having this kind of shard manager, it improves abilities in multiple ways. First is the SM is a shard replica across 4 domains. And SM's task control collaborates with underlying cluster manages to selective delay inhibition mode container lifecycle operations that are unsafe. And SM protectively prevents for non-efficient events such as hardware maintenance and kernel upgrades. And at the same time, SM ensures that no requests are dropped from an application during a graceful primary replica validation. We'll talk about that later. Yeah, actually, let's talk about the validation. When the orchestrator decides that a primary data shard needs to be moved to the new primary, it first tell the new primary to prepare to add this shard, and then tell the old primary to prepare to drop this shard. And after that, the orchestrator adds the shard to the new primary. And when this step is done, the orchestrator tells the service discovery that where the new data is, and only after the service discovery system confirms the data transfer has been completed, the old primary will drop the old shard. And let's see, and there's a lot of for the PWB, they added many constraints to the systems. Like you can reach out to about and this is some examples of spacing and hard placement constraints and soft goals using the rebalance API. They also just give some optimization for the constraint solver. First is the shard manager divides a large application into partitions, builds a small optimization problem for each partition separately, and it solves them on multiple machines in parallel. A second is we configure rebalance to use local search instead of MIP to solve each partitions organization problem while meeting our required time constraints. And the rebalancer has communicated many domain independent improvements to current local searches. And SM allocator provides domain-specific knowledge to guide rebalancer to further accuracy in local search. This gives a constraint solver the ability to scale. And for the whole system scalability, they realize that one SM controller is not enough for the whole system in the Facebook. So they have, in practice, they have many control planes with many partitions, and is controlled by application manager. So this the shard manager itself is sharding. They really didn't talk really much about it. Coming to the evaluation, is it really widely used? Yes, the answer is yes. We can see from the picture that it's first developed in 2012, and right now the usage increased to over 4. I don't know how many case machines, but they do mention that in Facebook, by the time this paper is published, there's 54% of applications and 34% of servers are built on top SF. And let's see the scalability result. From those two pictures, we can see that the servers and the shards can be scaled upon the servers, upon the number of servers. And there's also not only geo-distributed mini applications that are deployed on the mini SM, but there's also some more regional mini SMs. It can be scaled both on regional and geo-distributed system. And one thing to mention about is availability. From this picture, we can notice that with Facebook's SM, the availability during time is 100%. And if there's without the graceful mitigation, it drops to 98%. That is also that is already unacceptable. But if there's without the graceful mitigation and without the test controller, it drops to about 88%. That's horrible. And it also have some other evaluations, like in this picture, in the figure 18, we can notice that if the shard moments happens more like happens during the time when the client request rate is dropped, and in the same time during the mitigation, the client error base is not increased. It still have some error, but it's not related to the shard moments. And from the second picture, is as a shard manager mitigation geo-distributed application shards across regions to handle failures. We can see from here. Well, when a failure starts, the latency starts and the mitigation starts, and after a short amount of time, it moves to a new shard, and after the failure has been solved, it move back to the old shard, the optimized shard server, and this thing drops down. And in figure 20, we can see that during the number of DB shard moves, the number of application shards also moves, and the latency increase. In figure 21st, this is a result of scalability, and we can notice that from if there's a 75K shards on 1,000 servers, it resolves the number of violations at a speed, and it's and when the shards are scaled and the servers are, when the shards number grows up, and if the servers number also grow up, the rate of solving the problem is actually reduced. So it isn't actually an increase. So it is scaling with solving the speed of solving the violations is scaling with the speed of servers.
Yeah. So you need when you have bigger system, you need more time to solve the problem, essentially, right? So the violation is the constraint violations. So if you don't give it enough time, you don't solve the problem correctly. You break some rules.
Yeah, and the figure 22 is about the for optimization that they mentioned in the paper. We can see that an optimized system can solve the violations way faster than the baseline without a optimization, without those four optimizations. Yeah, sorry. And in figure 23, we can see that SIM balance. This shows the SIM balance mode in an ever-changing environment. We can see that if the shard mode, when the shard starts moves, the CPU usage increase, and when the shard moves are completed, the CPU usage drop down, and the shards start moving whenever the violation they detect a violation in the system. This is pretty much about this presentation, and this is introduction paper for the SM shard management manager from Facebook. They didn't actually compare their system to others. I also don't think they can compare their system to other systems, like having the same amount of servers. And that's it. Thank you.
All right. Yeah. Thanks. So I guess I want to do a quick recap, right? So so this shard manager is okay, I lost the paper. I'll do it by memory. So this shard manager is the Facebook's way of managing this sharded applications, right? I think the paper tries to motivate itself by saying that like there is no good like universal way to manage these types of sharded application, because of like I don't know, they have different APIs, different ways to program, different things that they care about. They also talk about the fact that a lot of the systems for some reason don't care about the plant maintenance, which I kind of find strange, and don't care about a lot of the shard management systems are designed for data center only, and the shard manager is kind of a global system, right? So it can work at the data center level, which I think they call a regional setup. So like when you have regional setup, you have all of the shards, which by the way may be replicated in other data centers, but they're managed independently in each region, right? So if let's say a copy of a shard, like a replica, fails in one region, that regional deployment will find a new machine in the same region. But they also talk about the geo-distributed, and apparently that's kind of an important use case for them, where the shard placement and essentially the life cycle of all of the replicas in the shard is not constrained by a regional boundary. So in a geo-distributed way, they can start with a shard having a replica in one region, and then using this shard manager, they can migrate this replica to another region and maybe migrate it to another, and so on. So they potentially can build systems that like adjust to the locality, maybe like follow the sun kind of workloads, potentially, right? So that's another important use case that they claim that other systems don't have. I think for the rest of the paper, like they don't really give that much details about how they actually implement. They provide a few details on the APIs. What was interesting is kind of to see the constraints that they place, right? So every time a shard needs to be placed somewhere, like a replica of a shard needs to be migrated from one place to another, or just like another replica created, you have to solve for these constraints, ranging from hard constraints, which would be like, hey, give me a machine that can actually support this, right? It's very bad idea to put I don't know, a 100 gigabyte shard on a machine that only has 50 GB of space left, right? Or to place a shard with some hot object that requires like a lot of maybe computational resources on the machine that doesn't have that many cores available. So there are like these hard constraints about the capacity, but there are also a bunch of soft constraints that they talk about that range from things like geographical preference, right? Maybe you want the shard to have a copy in some region because it's being used there a lot, and it's kind of your ideal preference. But if for whatever reason you cannot find that spot in that region, maybe you can go to the next best region or something like that, right? So these are not hard constraints. These are soft constraints that you can violate if you absolutely need to, but you'd rather not. And yeah, essentially the solver is trying to solve for displacement and find these constraints. I also found it kind of interesting that they use Zookeeper for pretty much their failure detector. Like if the application fails, the Zookeeper will know it, and if the application server fails, right, the Zookeeper will know it, and it will communicate to the orchestrator, and orchestrator will know that things need to be fixed in one way or another. So yeah, I like Zookeeper. But it's I don't know, I think it's aging. So it's kind of interesting that they mentioned that, and I also wonder how well it can like scale. And yeah, speaking of scalability, their shard manager is sharded. So it's not one kind of monolithic system, even though it tries to be like all-encompassing, right? Geo-distributed, manage shards that cross the regional boundaries, data center boundaries. It's still sharded, right? So it's not like one monolithic. It's a bunch of things that cross the data center boundaries, but they're not, they only know about, each of them only knows about kind of a subset of the shards. And they do have a layer that sits on top that kind of coordinates and orchestrates them. So yeah, the shard manager is sharded. Yeah, that's also nice. Yeah, I guess we